Hello everyone. In this video we are going to talk about image segmentation using K-means clustering. So I talked about K-means clustering in videos of SciPy under my playlist Machine Learning, but here I want to talk about using the CV2 K-means method. So K-means is also available under OpenCV, and we typically use it for color segmentation in an image. So here I need my NumPy and OpenCV. I read an image in that has several different fruits in different colors. And then later I'm going to use my CV2 K-means method for clustering and segmentation, of course. Now this function has 6 different inputs that you have to provide. The first one, the samples, the data, and it should be of type float32. And it should be only basically a single matrix. It cannot be like an image, a multi-dimensional, a three-dimensional matrix. So the first thing you do here, as you can see, I'm reshaping matrix into something by 3, right? So 3 columns and so many rows. And since I don't know how many rows it is, one of the things that you probably have seen in many of the code, they use a -1. -1 when you use it in NumPy or OpenCV means I don't know the dimension, you figure it out for me. Okay, so here I don't know how many basically rows I should have in this reshaped version of the data. So I'm asking NumPy or OpenCV to find that out. So these 3 columns are the 3 channels. And now if I look at the size of the Z, right, it's probably the number of rows by the number of columns of the original matrix. Let me just show you that. So you see, this is this number. 415,548, right? Which is probably, as I said, the number of pixels in width and height of the image multiplied. So by that -1, I'm asking the software to provide that number for me. So that's the meaning of that part. Then I convert it into float32. I'm doing a typecasting here. So that's the first data you have to provide. Then the number of clusters, which is one of the most important things in OpenCV. So you can change this number and you're going to see different results. The next one that is in almost any code that you find online, it's always a none. And most of the websites fail to provide what is this none. And I had to dig a lot into it until I found that it is called best labels. So it's basically an initial thing that you have, the best guess that you have for the labels initially. If you know that. If you don't know that, you just say none. Then you have a stopping criteria or termination criteria, which could be a tuple of 3 things, or you can provide them separately. The first one is epsilon, which is basically the amount of change in the location of the centers. The next one is the max iteration, or it could be basically some of the 2. In my case here, I'm using both of them. So I'm saying an epsilon of 1 pixel, no more, no less than 1 pixel is accepted for stopping, and then at least 10 maximum iterations, right? So that is my stopping criteria. Then you have the attempts. So this attempts means I start my centers and labels random or using the other method PP, which is based on a different algorithm by 2 authors. I can provide the names, but it's not necessary here. So either start your centers randomly or start them based on a specific algorithm, and then change that and redo it and redo it and redo it. How many times? 10 times, and then return the best results. And how would you determine the best result? I'm telling you in a second, but this is the number of attempts, means changing the centers by one of these 2 methods, which is your last parameter, the flags, and repeat until you get the best results. Now, what are the results? The first one is compactness, which is sum of the square distance of each point to their corresponding centers, all added together. And the higher this, the lower this number is, actually, it should be lower. The lower this number is, the better the outcome is, right? Because when the data are close to their centers and the clusters are very compact, this number is going to be low. When the centers are not well inside the clusters and the clusters are not showing small standard deviations, right, in all directions, then this number is going to be high. So the lower this number is, the better the outcome would be. So it will run a bunch of attempts until this number is the minimum and then returns that. Then you have labels. So if you have, let's say, 10 classes, then this number is going to be 0, 1, all the way to 9. So, right, each one of them corresponding to one cluster. And then, of course, the location of the centers. So these are all the outputs and inputs of this function. You provide it, and then it gives you the centers, and it gives you the labels, right? And then what you can do with the label is you can use this flatten method, which you know that is what the vectorization, right? And here you're converting your centers into the uint8 units, okay? And then here I'm showing this res2, okay, which is reshaping the results of the labels into image shape, right? So this res, that, as you can see, it is saying center, labels, flatten, and then reshape. What are these several lines of code are doing? So the goal here is to create an image where the image has only 10 values in it, only 10 values. But remember, this label is like so many rows that 514,000, so many by one. So if you want to use the labels as index for the data in the center, you cannot use it. So the first thing you need to do is to flatten it. And by flatten, you are getting rid of the extra dimension of 1 that you have in the label. So it is just going to have 1 dimension. So now you can use label as an index. So if you want, I can add that for you here. This removes the dimension of 1 in label and allows it to be used as index or indices, right? So here these act as indices, right? And then these indices are only from 0 to 9, and as I said, the center has the RGB values in 10 rows, right, for the 10 centers. So this res is going to be what now? Is going to be a giant matrix which has that 514,000 rows by 3 columns, right? And basically in each row of that, you're going to have one of the values of these 10 centers. So basically you're propagating the data of these 10 centers to what? To all of the pixel locations in the image. Each pixel, depending on it belongs to which cluster, which label, will be assigned the value of its center. That's what you're doing basically in these two, in this single line. What I'm doing up here is I'm converting them into uint8 because I want to convert it into an image. So I convert the RGB values of the centers into uint8 format because remember, originally they are converted into float 32. So I'm putting them back to uint8. I'm assigning the values of the centers to all of the pixels here, and then I'm gonna reshape that huge vector, which is 514,000 by 3. I'm reshaping it back to the image shape. So now it's going to be like 400 by 600 by 3. So it's going to be a real image, a 3-channel image. And then I'm going to show that results of the K-means as well as the original image. So let's go ahead and do that. And here I start with a small number of clusters, see what happens. So here is the original image on the right, and then you have the segmentation on the left, and as you can see here, I don't have enough of clusters, so it is going to tell me that kind of this lime and the apple and this plum here, even the grape and the leaf and these cherries, they are kind of like belonging to one or two classes, right? So you see that it is not really doing a good job, right? And it's kind of mixing the green color here and let's say here this bright red or dark red color or something, it kind of counts them as one cluster because I don't have enough of colors here. Clearly, I need more than 4 colors to go ahead and cluster this. So I need to bump up the K in this case. And let's say if I go with 10 this time, I should have a lot better results. Now, if you look, now I have much better results, right? If you look at this clustering, this is way closer to the reality. Still, I have some misclassifications here. You see still the parts of the lime and the top of this plum are considered as like one cluster. Now the leaf and the lime kind of, in terms of color, they do belong to one cluster, but this area here, clearly that's not necessarily the best way, right? But you see now that I have 2 classes of red color here, and my grape, my apple, my cherries are being a lot better classified and segmented, right? In general, the color alone is not the best way to do segmentation. You also need the spatial information, X and Y and so on. But this can be a starter point, right? And here I go with 12 clusters. And now it starts to kind of add a different color cluster for these areas that the light is kind of shining on them. But the problem here is now you start to get what? If you look at the areas that you had like one cluster, now if you look at the banana or the lemon, you see that now you have several clusters on the same object. So now you're overfitting clearly. Okay, so now the effect of the reflection and so on are considered as a separate class, but now you're over segmenting the homogeneous regions and making them several classes. Like here, at least you are making this banana like 4 classes or so, which is not necessarily good. So you always need a balance and a good optimum point for K, and that could come from this compactness measure also, which you can print it, right? So but the thing is, this compactness measure always goes down as K goes up, but after some time this compactness measure, as I showed you, is not going to go down significantly. Okay, so let me go ahead and print this compactness also for you, right? Let me call it compact instead of red, which is not necessarily the best name. And let's say print compactness equals, and then this guy, right? Let's look at that for K of 4, which as you can see, it is this number here. It's a big number, right? It is like 792 million. Now if I go up to 8, this number should definitely go down. And you see 8 is kind of good balance here, although again, I'm not gonna have best things, but it's a well balancing. So now that 700 is down to 336, so it's reduced by more than 2. And then here I bump it up by 10 times instead of 2 times, go to 40, which is definitely gonna give me very good things, right? But probably overfitting. So let's take a look here. Right now, as you can see, this shaded area is very beautifully clustered as its own thing, and it's not the same color as lime anymore. So it is getting closer to the image itself, right? if I have as many as the number of pixels clusters, then that's basically an obvious clustering, right? So you don't want to go that far up, but now you can see that I have some extra contours that are showing up. Now let's look at the metric here. So the metric is 105 and this one was 792. So the factor between these two is what? Is about like 7.5 or something, while we bumped up the K parameter 10 times. Remember here, we bumped it up 2 times and the reduction was more than 2 times. Here, we are bumping it up by 10 times, but the reduction is about 7.5. So you clearly see the slowing down in the reduction of the output while the K is continuously going up. And if you can find an elbow in that plot somewhere, and you can find a fast reduction region separated from a slow reduction region, then the point, the K that is separating those two could be your best K. So hopefully this video was useful to you. I will see you in my next video. Thank you.